Okay, so we just derive our tangential velocity, okay, and that's the only velocity component, right, that occurs together in the vortex flow. Alright, so just a note also to know that when we talk about the velocity vector, it is not the streamline itself. Okay, so what does it mean is this. If I have a vortex, this is the point, I have a vortex that's flowing around this direction. This thing that I've just drawn, right, is the streamline. Okay? But the velocity vector is always tangential to the streamline. Okay, so that's what this statement is telling us. Okay? So the component and the streamline is two different things. Yeah? Okay, so this is what you must distinguish. Okay? So like what I say, right, since we are looking at a polar form, okay, that means we have VR and d theta. Okay, then even for the stream function and the velocity potential, we must be able to express them in terms of your VR and your b theta. Okay. So how do we do that? Alright. The first thing is that for VR, okay, it's always equals to 1 over r multiplied by the partial differential of the stream function over d theta, or is equals to the partial differential of the velocity potential over dr. Okay? And the next one, right, to find v theta, okay, is equals to this form here. So if you guys can recall, right, for Cartesian coordinates, where we have u velocity, is a function of both my stream function and your velocity potential. Do you guys remember this? You did two examples, right? If you know u, right, you can find v. If you know v, you can find u also. If you have stream function, you can find velocity potential, okay, because of the relationship that we have. Yeah. So it's the same for VR and v theta. Okay, it can be expressed in terms of both the phi, okay, and the psi. Okay, that means the stream function and the velocity potential. Okay. These two equations is extremely important. Okay, because as I said, most of the time we don't deal with u and v. Okay, because most of the flows that we deal with, right, are all circulatory. Okay, so VR and v is very important. Okay. So since we already know that VR equals to Vz equals to 0, okay, and your v theta equals to k over r, that what we have derived earlier on. Okay, so k again is a vortex strength, r is a radius that we're looking for. Okay, from here, right, if we know v theta, let's look at this equation. If we know v theta, it means we can know what's our stream function. It means we can know what is our velocity potential also. So for example, right, if I want to find the stream function, okay, I can just do an integration and I can answer it. So this is a definition, okay, but in the sense, it's an equation that you can want to memorize if you want. So for free vortex, okay, your v theta is equal to k over r. If you know what's your vortex strength, you can find the v theta. If you want to find the stream function, it's always equals to the vortex strength multiplied by the ln of the radius of the vortex. Okay. But there's no need to memorize. I think you should learn to derive this yourself. Okay. So we can do for the stream function, therefore we can also do for the velocity potential. Alright? So can you all try? How do we get the answer for the velocity potential? What would be the answer equals to? What would be your phi equals to? Can someone try the math for me, please? You have v theta as k over r, right? So you have k over r equals to 1 over r delta phi over delta theta. How do we get our phi now? What is phi equals to? Can we cancel the r here? Can, right? So we have what? K delta theta equals to delta phi. So phi will be equals to what? Okay, so this is not fluid mechanics, this is math. Okay. Everybody get the same answer as me? Okay, so if I do the same thing, right, I'll get k theta here. So a vortex, right, is made out of many if I look at a huge vortex, right, it's actually made out of many different stream functions there. Alright, so each one of them has the same stream function value. Okay, like what we did in the past, when we talk about streamline, every streamline has one stream function value. Okay? So, important points to note is this. Okay, obviously if b theta equals to k over r, okay, as your r goes to become very, very small, your b theta becomes very big. Okay, so it's really like just like a tornado. Okay, you have an eye at the center there. Alright. Okay. So to find the constant k, that's what we are looking for. Okay, because we want to know what's the vortex strength. What's that vortex strength equals to? Okay, how do we do that? Okay, so we can use our circulation to do the answer. Okay, so last week, right, if you guys can remember, there's this theorem that I mentioned, Stokes theorem. Can anyone remember? No, right? Circulation is equals to what? The closed integral of the velocity times the line integral, right? What is it? What else is it equals to? Anyone remember? Really, no one remember. What else is our circulation equals to? It's equals to the vorticity times the area, right? And the vorticity is perpendicular to the area. Remember this? Oh, you guys are worrying me, no? Integral of my omega z dA. Remember this? I put an n factor here. I say it's a normal component. Yeah. This is a Stokes theorem. So that means, right, if I know the vorticity, I know the area that I'm looking for, I can find the circulation. Otherwise, if I know the velocity vector that I'm concerned about, okay, and the length scale that is going around, I have to find the circulation. Okay? These are it. You guys need to know this. We are not joking. So you need to know these two equations. It's very important. Okay. So this is the Stokes theorem. Stokes theorem simply tells us that these two equations is the same thing. It tells us the circulation. Okay? Now, if you look at this vortex flow here, I think you guys will follow me, please. Some of you guys, I went to ask around, I say you all cannot catch up last week, this week also cannot be bothered already. Don't do that, okay? You need to make sure that you can try to catch up, because these things that I say, right, I don't have time to repeat myself. You can ask your friends from last year. Right? So we don't have time to revise it, so you need to build on the knowledge.
So you can repeat what you read?
Huh? This is, okay. Sorry, my handwriting is much tricky. Yeah, I put a normal vector here because it represents that the A will be x and y. Because you're looking at the z vorticity, right? So x and y is perpendicular to z. Remember what I said about this? If I say now I don't have omega z, but I have omega x for example. So what your dA will be equals to? Dy times dz, right? Okay, so this is the Stokes theorem. Okay. So if you look at this circulatory flow, or this vortex flow here, okay, what is your V vector equals to? Is it UVW or is it VR V theta? VR V theta, right? But what is VR equals to? Huh? What is VR equals to? 0, right? So the only vector, the only component that I have for this velocity vector is my V theta. Okay? Now what is this dl equals to? If I'm moving in the circular motion, what is this dl equals to? 2 pi what? 2 pi r, right? Because we're looking at the circumference. Therefore, right, for us to get this equation, it becomes very simple. It's just d theta times 2 pi r. Okay? Last week when we derived, we are looking at a square box. That's why it's length times breadth, length times breadth. Yeah, your x coordinates, your y coordinates, your x coordinates, y coordinates. But in this case, because we're looking at a circular flow, okay, that's why the circumference will be your dl. Right? So in exams, right, they will ask you if you have a vortex flow around a sphere, for example. Alright, then it will not just be 2 pi r anymore. Okay, if it's going past the surface area of the sphere, right, then it will be 4 pi r squared. Okay, so it depends on where the flow is going past. Alright, so in this case, because it's a 2D flow and it's a circular flow, that's why it's a 2 pi r here. Okay, so that means we can find V theta. So V theta is just equals to the circulation over 2 pi r. Okay. So just now, right, we mentioned also, right, d theta is equals to what? K over r, correct? So can you find what k equals to? Okay, we will know that k will be equals to minus the circulation over 2 pi. Okay, so this helps us to find the circulation, or the vortex strength, excuse me. If you know the circulation, okay, you can find what's the vortex strength first. Okay, so just now we know these two functions here, your stream function and your velocity potential. Therefore, right, instead of writing my K vortex strength, which I don't know, okay, I can express them in terms of my circulation. Okay, so this is just a different form. Just instead of writing K, I write as capital tau over 2 pi. Okay, now what is your R and theta equals to? Sometimes, right, if you still insist on presenting in the Cartesian form, okay, we can write this down. Because R, remember that's how we do x squared plus y squared equals to R squared, correct? So therefore, R will be equal to square root of x squared plus y squared. Okay? And then we know that tangent theta is equal to y over x. So therefore, theta will just be equal to tangent inverse y over x. Okay, so if I want to explain this in words, right, it simply tells us that for a free vortex, okay, the vortex strength is defined as the circulation above that point. Okay, if I know the value of the circulation, okay, I can find the vortex strength. Okay, now the thing is, right, for vortex, right, it doesn't happen just like one vortex. Okay, it happens when there's a lot of vortices that we're looking for. For example, right, if you see an aeroplane that's flying in the clouds, right, you see all the trailing vortices. That's made out of infinite numbers of vortices, right? So how do we actually quantify that, or what's the implication of that? Okay, so there's something that we can do. Okay, that is called the Biot-Savart law. Okay, so the Biot-Savart law will tell us something that when you have a vortex, right? Okay, it sort of induce something, and that induce something is actually your induced drag. Yeah, and when there's induced drag, right, you actually have this thing called a downwash velocity. That means, right, you reduce the velocity factor. Okay, so your angle of attack will actually decrease. Okay, how do I actually do this, right? Let me just try to explain this to you. So if you now align, okay, infinite number of point vortices together, I think the spelling is wrong. It should be VORTICES, but maybe some people prefer this. Yeah. Right, VORTICES, vortices. Okay, so if I align all these vortex together, okay, we sometimes call it as a vortex filament. Okay, so that means, right, there are many, everywhere along a straight line, there are many points where there's all the circulation strength. Okay, and every circulation strength that we have, right, will result in this thing called a dV. This dV, right, is known as a downwash velocity. Okay, either we call this the downwash velocity, okay, or we call this as the induced velocity. Okay, both are the same thing. Okay. So as a definition, okay, for us to find out what is this dV equals to, okay, in relation to all the circulation strength that we have. Okay, for example, right, at this certain point here, I have a circulation. Okay, this circulation will cause an induced downwash velocity at a certain r distance away from me. Okay, like what I said, right, if you have many circulation points, okay, that means the dV is a summation total of all the circulation that I have. Okay, so as an equation, okay, this equation just tells us that to find a velocity downwash, okay, an induced velocity, okay, is equals to this equation here. Okay, now what does dl stands for? It means a certain length scale, a certain part of the vortex filament. Okay, what does r stands for? R stands for the point of circulation to the point of interest that I want. Okay, that means any point that I want, right, that has an induced velocity. Okay, I mean, to put it simply, this is when I mentioned this before. So when you take off an aircraft, right, you always have a queuing time, right? What's that for? It's for this reason here. Because when the aircraft takes off, right, for the trailing vortices for the side of the wings, you have all these vortices here, and all these vortices will cause a downwash velocity. Now, if you have a small aircraft that's taking off before the big aircraft, right, you don't wait long enough for this thing to dissipate away. What happens? When you take off, right, you'll come crashing down. Because the velocity is very strong. Yeah? So that's what it's trying to tell us here. So as engineers or as designers, right, what we're trying to do is to reduce this dV here. How do we reduce this dV? Anyone? We do winglets, right? You have all your wings, right? The winglets at the end of your wings. Okay, that is to actually disturb the induced vortices here. Okay, to reduce the circulation, reduce the circulatory strength, such that the dB is smaller. Okay, so the implication is not just for other aircraft that's behind you, but it's also for yourself. Later you will learn, right? As you have higher dB, you have higher induced strength. You have higher induced strength, right? You have a lower lift. Right? That's not what we want also. Alright? So that's why for us, okay, this dB is undesirable, right? Okay, so we need to reduce this value. Okay, so this is the dB, right, for a particular point. That means from a certain point dl, I know a certain dB. Yeah, but if you can imagine, right, I got millions infinite points of dl here. Therefore, right, to do a summation total of this, what do I need to do? I do an integration. Okay, I do an integration from negative infinity to infinity. But rightfully, right, it's just from minus b over 2 to b over 2. That means from one side of the wing to the other side of the wing. Okay, so a wing, right, later we will learn also. At the center of the wing, we always say is equal to 0. Okay, if you go to the right hand side of the wing, right, it's b over 2. Okay, if you go to the left, it's minus b over 2. Right, because the wingspan is measured in terms of what? B, right? So it's the total wingspan is b. At the center is 0. So to the right is b over 2, to the left is b over 2 also. Okay, but from an equation point of view, we always write as negative infinity to positive infinity. Okay, so just think, okay, this cross here is not multiplied, okay, it's a cross product. Why? Because L, right, is a length scale, that means it's a certain location. R is also a certain location, that means we can actually define whether is it to the right, or is it to the left, or is it to somewhere above and things like that. So that means R, right, is actually a displacement also. So both my dl and my dr are just velocity vectors. Alright, so we cannot just multiply them together. We can actually find out okay, the cross product of these vectors then. Alright. Okay, so where do this vortex filament appear? Okay, this line that I've drawn appears. Okay, so if you consider a finite wing, okay, that will come maybe next year. Okay, what you will see is this. Okay, you will see that across the wing surface, okay, you will see all these vortices here. This is very similar, right, to what I mentioned before last week on the boundary layer. Remember I said when a laminar flow develops over the surface of the wing, yeah, we have this point called transition, then the boundary layer will separate. When the boundary layer separate, what you have? You have laminar flow, right? Okay, you have all the vortices. Yeah. So these are all the vortices then. Okay, if you can quantify all these vortices by the circulation strength, okay, we can actually calculate what the ground motion is. Understand what I'm saying? Okay, so the challenge is this. If, right, I got only 10 points, for example, across the wing, then it's easy for me to calculate, right? But the answer will not be accurate because 10 discrete points along the surface of the wing is probably not enough. The better way for us to do it right, is to have many points there. The more points I have, right, the more circulation strength I can get, the more downwash I can calculate, the total sum will be more accurate. Yeah? So the challenge is for us to actually find out what is the total sum of the circulation that I can get across the wing. Okay? And if you notice, right, I only draw one line here, okay, where it tells us the circulation strength. But you can imagine along the wing there should be many vortex filament. Everywhere on the surface is all vortex filament, right? Because there's so many vortices that you see. Okay? So the good thing is, right, I can actually start to simplify a few things. Okay? There's this theorem called the Helmholtz theorem. Okay, it just tells us that we can assume, okay, that for every line that I have along the chord length, okay, the vortex filament has a certain constant value, okay, to the vortex strength. Okay, the second thing is this: we cannot end the vortex, okay, at the end of this wing here. Okay, somehow it has to dissipate away. Alright, so how does it actually dissipate away? Okay, if you think about this, right, the only way for this to dissipate away because of this Helmholtz theorem, right, is this. You can see that the circulation strength will go from the surface, okay, and then it trail downwards by the wingtips there. Alright? So this is the very famous thing called as a horseshoe vortex. Okay, because it looks like a horseshoe. Okay, so it's called as a horseshoe vortex. Okay, so this is known as the starting vortex. We'll revisit this again. Okay, the starting vortex is very important for something to generate lift. Okay, but this is just telling us that along the surface of the wing, alright, because of stress, because of friction, because of viscosity, okay, we have all these vortices here. And if there's an infinite number of vortices, right, we call this as a vortex filament. Alright? Now the problem is that the vortex filament cannot end just at the wingtip, it has to actually dissipate away. Okay, so that's why it trail downwards, okay, from the wingtips. Alright? So this is what you see now. You see a aircraft flying in the clouds, right? You see all the trailing vortices? Yeah, this is what you actually see. Okay, so actually at the end of the day, right? Okay, as I said, we will calculate this thing here. The vortex that's bounded by the wing, okay, will eventually become a tip vortex. Okay, and eventually further downstream, right, the two tip vortices will actually join together, and they are known as a starting vortex. This starting vortex is what we'll learn in the next week lesson, right, where we talk about the Coulthard-Tchaikovsky theorem. Okay, where if you know the circulation strength, you can actually find out what's the limit equals to. Okay, so I'll come back to this later on. Right, so now the interest of this vortex, right, okay, is to know what is this downwash equals to. Okay, can you please highlight this? The focus of this chapter, right, is just to know how does all these vortices result in a downwash. That means result in a certain downwards induced velocity. Okay, this is something that we must quantify. Okay, so there are some examples here that you will know about for wing tip vortices. Okay, so this left hand side is actually a CFD simulation. Okay, not very clear, but really, I think the contours, right, is just showing the vortex strength. So you can see that the wing tip, right, okay, has a lot of vortex strength. This is straight color. The other one is just a picture that I took from the internet. Okay, if you actually inject some dye, right, okay, you can see that for aircraft that's taking off, you can see a lot of vortex spinning also. Okay, so this one presents, right, a very large downforce, really. Okay, so that's why aircraft doesn't have to wait before they fly off. Okay, just for this to dissipate away first. Right? So how does this presence of these trailing vortices, right, affect the performance of aircraft? Okay, so this is something that you look into. Okay, next year when we talk about finite wings. Right? Okay, so how do we actually start to quantify this value of velocity, or we call it induced velocity? Okay, so if you just imagine, right, okay, this is perhaps easier to see. Okay, you have an aircraft that's taking off. All these are your trailing vortices. Okay, and here, right, you can see that all these trailing vortices cause certain downwash, you see here. Okay, so the downwash is undesirable, as I said. Okay, why? Okay, because A, you will reduce D. Okay, B, right, you will reduce the effective angle of attack. Okay, that's why all the wings that we have must have a camber. There must be some geometrical angle at attack already right before you take off. Otherwise, you will not be able to take off. Okay? And these things, right, if you have an induced velocity, right, velocity and pressure is always related to one another. Okay, so it's also called as a pressure drag. Okay, that's over the surface of the wing. So the thing is, right, these vortices are actually wasted energy because it does nothing except to cause an induced downwash. Alright, so that's why we must consider this as drag. Okay, and we need to sort of reduce this value here. Okay, so how do we actually get the downwash velocity? Okay, so let's try to do this analysis together. So I have a wing here. Okay, if you can see properly, right, this is a rectangular wing. Okay, so this is from the top view. Okay, so you can see that U is coming in this direction. Okay, the span of the wing is this direction here. That's your V here. Okay, so the vortices are coming down in this direction and also in this direction here. So the center of the wing is V equals to 0. Okay, that's why on the right hand side is V over 2, on the left hand side is minus V over 2. Okay, let me write it down. It's V over 2. Okay, so at the center is equals to 0. Okay, now if I tilt this wing to a certain angle, let's say I tilt into this direction here. Okay, I have the same thing here. Now the good thing about such an analysis is this, because we assume that the left and right hand side is symmetrical, so we can just do the analysis on the right hand side of the wing first. Okay, so this diagram, right, is the same as this diagram here. Okay, just as to the different angle here. So the trailing vortices will always go downwards away from the wingtip, okay, until it dissipates away. Okay, so let's say right now I have just look at the right hand side of the wing. Okay, I have this wing here, and I want to see, right, how does the circulation on the trailing vortices affect the downwash value. Okay, so how do I do that? So if you think about this equation here, okay, so This point P, okay, is a circulation point. Can you write it down? It's a circulation point. Any point. Okay, that's why I put a capital H here. Right, so it's just a distance away from the right hand side of the right wingtip, excuse me. So P is just any point. Okay, so it's just an arbitrary point. Now ds is the point that I'm concerned about. That means I want to know what is the downwash velocity happening at this point due to point P. Okay, so it's all arbitrary, doesn't mean anything at all. It's just a certain location. Okay, so H is a certain value that we can find. Okay, but more importantly, right, okay, we should be concerned about B over 2 because that's the span, half span of the wing that we're concerned about. Okay, so H is just a certain distance from the wingtip, okay, to the particular point that I'm interested in. Okay, ds, okay, is the point where I want to find out what is that downwash equals to. Okay, now before we can do anything to the equation, the first thing you can do, right, is to do some trigonometry, because if I have a certain point P, right, to my point of interest that I'm concerned about, okay, I can actually put an arbitrary angle here. Okay, so in this case, right, we put as beta. Okay, so these are all just constants that we can consider. Okay, so you can see, right, this is almost like a right angle triangle, right? So you can say if this distance, right, P to ds is my r. Remember R, I say R is the distance from the circulation to the point of interest. That is where the induced velocity is happening. Right, so this is my R. Okay, so if I look at this as a trigonometry, right? Okay, I can say cosine beta is equal to H over R. If cosine beta is equal to H over R, right, therefore H will be equal to R cosine beta. Right? Okay? And this side here, right, is your S direction. So I can also know that tangent beta is equal to H over S. Okay? Sorry, tangent beta is equal to S over H, excuse me. Opposite over adjacent. Therefore, your S is equal to H tangent beta. Okay, there's a reason why I do a ds over d beta, okay? So, when I do a differentiation of ds d beta, right, tangent beta will become what? Secant squared beta, right? So I got secant squared beta here. Okay. Now, why do I do a ds, right? Really, it's because of this. Let me just go back to the previous slide first. I'll show you something. Okay, your ds, right, actually is the same as your dl here. Okay, they are both the same thing. Okay, just a certain length downstream of your vortex filament. Okay, so ds, dl is the same thing. That's why I must know what is my dl or my ds equals to. Okay, so based on the equation that we have, okay, you find that ds is equal to h secant squared beta d beta. Alright? Okay, so we did this also because, right, we are concerned about ds cross r, right? So we must know what is this equation here. Okay, if I have a vector that is ds, I got a vector that is r here. Okay, this theta is important to me. Okay, because you want to find the angle between two vectors, right? Okay, I only this equation here. Okay, so if I want to do ds cross r, as what the Biot-Savart law has said, okay, not only do I need to know beta, I also need to know what is this equals to. Now, what is this equation? What is this value equals to? Anyone? If this is beta and this is 90, what would this be equals to? 90 minus beta, right? Correct? So this is actually my 90 minus beta. Okay? These are very important, okay? So why is it important? Let's try to do something that we have done before. Okay, so we know this equation, right? A cross B is AB sine theta, where theta, right, is an angle between the two vectors that I'm looking for. Okay, so the cross product of two vectors is equal to another vector that we have here. Okay, now just like I mentioned, right? Okay, if this is beta, this is 90, this angle here will be 90 minus beta. Do you all agree? Okay, so what we want, right, for a cross product is this, is sine theta, right? So what is sine 90 minus beta equals to? What is sine 90 minus beta equals to? Anyone? Sin 90 minus beta is equal to cosine beta, right? Sin 30. Yeah, we just write this again. Here, press the calculator, please. Sin 30 is equal to what? Cosine 60, right? So that means sin 90 minus beta is equal to cosine of the value. Okay? So, let's look at the Biot-Savart law definition. Here, right, we have the total induced downward velocity is equal to the integral of the circulation over 4 pi multiplied by ds cross r over r cube, correct? Okay, so ds cross r, we can write this as ds cross r equals to ds times r times sin 90 minus beta. Okay, so sin 90 minus beta, if I simplify, right, it becomes ds times r times cos beta. Okay, now why do I do that? I do that because, right, it's difficult for me to integrate a vector. I cannot integrate a vector, but I can make use of the cross product of vectors, right, to give me 3 scalar values. So ds cross r just becomes ds times r times cos beta. So they become scalar values that I can integrate. Okay, so the equation here that we cannot integrate because it's a vector, okay, it becomes integration that I can just simplify. Because there's an r cube, right, I can then cancel off. So previously, if you look at this equation, I cannot cancel this r with r cube, yeah? Okay, because ds cross r is a one term on its own, it's a vector quantity. Okay, so I cannot cancel my r and r cube. But when I expand my cross product out into this form here, okay, this r and this r cube, then I can cancel off. Do you understand what I'm saying? Okay. Do you have to copy anything here? Anyone who understand why am I doing this? Anyone know why I have 90 minus beta here? Oh, you should be okay, yeah? Because it's a right triangle. Okay. Okay, so now, right, if I have just transform my cross product of two vectors into scalar values here, individual scalar values here. Okay, this is the magnitude of Vs, this is the magnitude of Vr, this is the cosine beta. Okay, I can then start to do some simplification to this equation. Okay, so how do we simplify this equation? So note that, right, okay, my dl and my ds is the same thing. Okay, so I just use as ds here. Can anyone recall what is ds equals to? Just now when you go to the two sides earlier, right, we found a differentiation for ds. What is ds equals to? H secant square beta d beta, right? Okay, so I can actually expand this as h secant square beta d beta. Okay? So like what I say, right, when you talk about negative infinity to infinity, okay, actually what we are doing is from one end of the ring to the center and from center to the other side of the ring. So for the limits for beta, okay, the most you can go, right, is actually from 0 to pi over 2. Okay, so from right hand side is 0 to pi over 2. If I want to do for the whole ring, the whole vortex filament that I want to consider, it will be minus pi over 2 to pi over 2. Okay? So take note, okay, if I say b over 2, okay, I want to translate it to Cartesian form, right? Okay, it becomes 0 to pi over 2. Alright? We will come back to this video when it's a finite ring. Okay, just think about this one. Okay, so can we just try to simplify this? Now, look at this equation. We have v equals to negative infinity to infinity of this equation here. Okay, so if you just consider one side of the equation, that means one half of the vortex filament. Okay, so the negative infinity and positive infinity will become 0 to pi over 2. we need this, okay, because we need to use this to find what's our beta equals to. Okay? So if I do this right, and I simplify, what I will get, okay, is this equation here. Okay? This becomes a very easy equation for me to do my integration. Why? Because my circulation is a constant value, my 4 pi is a constant value, my h is a constant value. So what do I have to integrate at the end? The only thing I integrate is cosine beta. What do I get when I integrate cosine beta? I get negative sine beta, correct? Okay, when I substitute my limits inside, okay, I can find that the total induced downwash is simply equal to my circulation over 4 pi h. Okay, so obviously, right, if I want to do for across the whole wing, okay, either I times 2 to this answer, or I do what? Negative pi over 2 to pi over 2. Alright? So if I do this, I can get answer as circulation over 3 pi h. So this answer here, okay, is an induced downwash for just one side of the wing. Okay, this is a total induced downwash for the whole wing that I'm looking at. So obviously h, right, can change. Right? H is any point that I'm considering. Remember the point P that I talked about? Right? H is from the wing tip to the point P. So if P changes, H will change. Alright? So these are the two equations that I have. Now the question is, that some of you will ask me is this: how do I get from this first line to the second line? Okay, so we can do an exercise together. Okay, so this is a cross product, right? How do we simplify to such a form? So this is the Bio-Savart's law. Okay, let's try to do this together and see whether you can understand what I'm saying. So this is ds cross r, remember? Just how 2 slides ago we said ds cross r equals what? ds times r times sine 90 minus beta. Just write down here. ds cross r is the magnitude of s is the magnitude of ds multiplied by the magnitude of r times sine 90 minus beta. Correct? So ds, the ds is just the magnitude, the r is also the magnitude. The sine 90 minus beta becomes your cosine beta. Correct? Therefore, right, from an equation that is cross product, it becomes this ds times r times cos beta. Okay? Now, we all also know what ds equals to, right? Just like you mentioned, ds is equals to what? H secant square beta to beta, right? So I can change my ds into h secant square beta d beta. Okay, we can do something else. Okay, we can actually change our r. What's r equals to? Can you go back to a few slides? You will see that r is equal to something. The very first few slides I give to you for the Bio-Savart's law, right? I say r can be just of beta also, right? So if I differentiate r, I can actually get h secant beta. Okay, so r will just be equal to my h secant beta here. Can you all go back to, let me count on. 3 slides before, you'll see that I have this equation where I say, right, my h is equal to r cos beta. Remember this? Correct? So if I do dh dr, okay, so what is r equals to? It will be h over cos beta. Correct? So that means my r is equal to h secant beta. Okay, that's where I get my h secant beta from r. Okay, so by doing all these things, right, okay, it helps you to simplify a few things, because if you see from here, I got a secant square beta, correct? I got a secant beta here. So secant square times secant becomes what? Secant cube, right? At the bottom, I also got a cube, correct? So that means my secant cube can be cancelled off already, right? I got h here, so I got what? H squared. At the bottom is h cubed, correct? So I'm just left with h at the bottom. Okay? So that's why the final equation I get is this here. So, by the second law, if you want to find the velocity induced right to the right hand side of the wing, it's really this equation that we written down in green. Okay? But the math to get to this answer right is a little bit more tedious. Okay, to get to the final answer. So I hope you all can distinguish between these two things. The math part and also the free mechanics part. They are actually different. Okay, it's quite easy to understand these values here, the velocity. Right? Okay, but it's quite difficult to get to the final answer. So you need to be strong in your math also. Okay, to make sure you can get to this stage. So as a way to do this right, in the exam right, I think this equation will be given to you. That means the balance of the law definition will be given to you. Okay? But because the h always changes, okay, there's no way you can memorize this equation because unless right, it tells you h is a certain value, otherwise right, we need to be able to integrate this out ourselves. Okay? Now, as I said, right, your h value actually depends on the point P that I'm interested in. Right, so therefore, right, a more accurate way for us to understand this is to know how is h related to the span direction. That means the span, the wingspan value that I have. Okay, so if you are you still copying? Okay. Those who are really tired, right? Just 10 more minutes, 20 minutes, I'll stop. This time, try the heavy lunch for us. I did eat my lunch because I know I'll be tired also. Can I move on? Okay, okay, so as I said, right, okay, this h value depends on the location that I'm interested in when I do my simulation. Okay, so if I look back at the same wing again, okay, what is h equals to in terms of the wingspan? H is just equals to b over 2 minus x. Okay, now as I said, right, h is measured from the wing tip to the point that I want. Okay, therefore x is measured from where? X is measured from the center of the wing, okay, to the point. Okay, so what does it mean is this? If I have a wing, okay, this is 0, 1. Okay, this is b over 2. Okay, so that means, right, the distance from here to here will be b over 2. Okay, h is measured from the wing tip to this point. This is h. So therefore, right, this will be equal to what? X. Okay, so h is always equal to half of the span, okay, minus x, where x is the distance from the center of the wing to the point where I'm interested in. Alright? So instead of writing h, right, as what we did in the previous slide, okay, we can write this as what? B over 2 minus x. Okay, so on the right hand side is b over 2 minus x. Obviously, if you look from the left hand side's point of view, okay, it becomes b over 2 plus x. So the final answer we get, right, we're going to find the total induced velocity. Okay, we add up the sum total, we get this answer here. So b over 2 plus x, b over 2 minus x is just a plus b, a minus b. So you get your a squared minus b squared. Okay. Okay, so with this, right, okay, we can actually try to understand or how to find the velocity, the induced velocity. So I just want to go through one more example. Okay, then we'll call you a day. Yeah. All right. So let's try the next one, the example that you will see in the next slide. Okay, now you have this case, right? Okay, where I don't talk about the wing first. Okay, it's just a circulatory vortex that I have. Okay, can I have your attention please? Okay, just one last question. Okay, so please understand that question. Okay, the question is asking us to find the induced velocity at the center of this circular vortex. Okay, okay, based on a certain circulation strength that I have here. Alright, so for us to find the induced velocity, okay, the first equation that you must be able to infer right from this question, okay, is this equation here. Okay, so this equation will never change because it's constant, it's a universal equation. Okay, the question is right now my ds and my r right is totally different from what I've just gone through already. Because what I just gone through is from a rectangular wing, yeah, and it's trailing vortices downstream, 90 degrees. But this case right now it becomes a circulatory flow. So then we must ask ourselves, what is ds? What does ds represent? What does r represent? Okay. So let me ask you guys, what does ds means to you in this case? Someone says circumference, very good. So the s becomes the circumference that I'm interested in. Okay, what about r? R is the radius.